For this video, we'll be going over perfect inelastic collisions, different types of collisions, and conservation of momentum as well. So, for this topic, first we'll just go over what a perfectly inelastic collision is. So, a perfectly inelastic collision is a collision where, I'll just draw it, but I'll explain it as well. A collision where kinetic energy is lost and after the collision, both particles move at the same speed. So in this depiction, particle B is at rest, particle A is moving, and then after, here, that was before, and then after, they're moving together at a new speed. So let's just say this is V naught and this is V1. They're moving together at a new speed. So that'll come in handy, so write that down. And then now we're just going to go over conservation of momentum and angular momentum. So angular momentum, the equation for angular momentum is L equals I times W. Okay, this is angular momentum. So now we'll go to last thing for this. I is moment of inertia. So moment of inertia equals mr squared, or integral of r squared dm, whereas omega, which is angular velocity, equals linear velocity, v over radius. So now we can go to the problem. It is number 17 of a 3-part set. So here's what the problem is. A solid disk of mass m and radius r is freely rotating horizontally in a counterclockwise direction with angular speed omega about a vertical axis through its center with negligible friction. The rotational inertia of the disk is mr squared over 2. A second identical disk is at rest and suspended above the first disk with the centers of the two disks aligned as shown in the figure above. There's no contact between the disks. The second disk is dropped onto the first disk, and after a short time they rotate counterclockwise at the same speed, omega final. So I know in this drawing I drew a perfectly inelastic equation as particle is hitting another particle, whereas this is spinning disks falling onto one another. But if you think about it, they're the same concept. So at first one is at rest and one is dropped onto the other, and then they both end up moving with the same final angular velocity. So just based off that, we know that because it's a perfectly inelastic equation, kinetic energy is lost. Okay, so now noting that, the question 17 asks us which of the following properties of the two-disk system must be conserved between the time the second disk is dropped on the first disk and the time that the two disks between rotating with the same speed. So, going off that principle about perfectly inelastic equations, that means kinetic energy is lost. So, it can't be A, because A is not conserved, and because kinetic energy is lost in this equation. So that rules out answer C as well. Next, we think about angular momentum. So for angular momentum, that means that angular momentum has to be conserved, which in an inelastic collision, momentum is conserved. So therefore, angular momentum is conserved, which is the only option that makes sense. So B is our answer for problem 17. Yeah.